So the final chapter is on work and energy. Okay, as its name indicates, we will relate work and energy in one equation. So the objective of this chapter is to apply the principle of work and energy that involve force, velocity, and displacement of a particle. And we will introduce the concept of power and efficiency. And finally, we will learn when we can apply the theorem of conservation of energy to solve kinetic problems. So to start with, we should define what is the work of a force. To have a work, you should have displacement. If no displacement, no work. Okay? And a force will do a work if it has a projection along the displacement direction. For example, if you look at the figure here, this is F. F can be divided into two components, one perpendicular to motion, one perpendicular to the displacement vector dr, and one parallel to dr. The perpendicular component will not do any work, only the parallel component will do a work. This is why we can define the work by the scalar product, because the scalar product will do what? It will do the projection of F on the displacement. So we can say that the elementary work of a force is F dot F vector dot dr vector. Now, if we apply the scalar product rule, we know that the scalar product of two vectors will give us the magnitude of the first times the magnitude of the second times cosine of the angle in between. So it's F ds cosine theta, and F cosine theta represents the projection of the force on ds. If the projection and ds are along the same direction and sense, then cosine theta will be positive because theta will be smaller than 90. And if f and ds, the projection of f on ds is opposite to ds, then we have that theta is higher than 90 and cosine theta will be negative. Okay, so this general formula can give you the projection of the force on the displacement. Then you multiply by ds, so you get the elementary work. Now, to find the total work, if you go from one position S1 to another position S2, what you can do to find the total work, you can integrate over the path of motion. Okay? Because as we said, the elementary work is F cosine theta ds. So in case one of these two are variable, in case F is variable or cosine theta is variable with S, then we should integrate over S to get the work of the force. Okay, so if I go from point 1 here to point 2, then the total work will be integral from 1 to 2 of f cosine theta ds. And in case f and both f and cosine theta are constant, I can take them outside of the integration and I get f cosine theta delta s. Now, we will start to develop relations for the most common forces. So to begin with, we'll begin with the weight. Okay, the weight is always vertical, downward. So if I take frame X, Y, and Z as shown, where Y is along the vertical direction upward, then we can say that the weight is equal to minus Wj. So this is the expression of the weight, minus Wj. And to find the work of the weight when we go from position 1 to position 2, we'll apply the formula. The vector weight is minus Wj. The displacement dr, since we are in a Cartesian system, we can decompose the displacement into three components: dx along I, dy along j, and dz along k. Okay? And now we do the expansion of the scalar product. You know that j dot I is 0 and j dot k is 0 because they are perpendicular. So you only have j dot j, which is 1, which will give you minus w dy. And now if you integrate between y1 and y2, you get that the work of the weight is minus w y2 minus y1. And please remember, the condition for this relation is that y is positive upward. So this is the condition. So if you choose y positive downward, then the work will not be minus w delta y, it will be plus w delta y. Okay? Anyway, always to check your answer, the work of the weight will be positive when the particle will go down, and it will be negative when the particle will go up. Why? Because if a particle is going up, then the weight will oppose motion, okay? And the work of the weight should be negative. While if a particle is going downward, the weight will help motion, so it will do a positive work, okay? So here, let us write if motion upward, what will happen? Delta y will be positive, okay? And as expected, if I replace in the formula, since I have a minus before, the work will be positive, negative, sorry. And the work is negative, since I have a minus before, okay? Which is the case I want, because as we said, when we go up, the work of the weight is negative. When we go down, the work of the weight is positive. And if I take delta y negative, then the work will be positive. And now I will just write it for you here. If I take y positive like this in the opposite direction, then the formula becomes, then in this case, the work of the weight, U is the symbol of work. The work of the weight will be plus W delta y plus W delta y. Why here it will be plus? Because when I go down, delta y is positive. When I go up, delta y is negative. Okay. Any question until here? So this formula, you can directly apply it. Whenever you have a weight, you can directly say the work of the weight is minus W delta Y when working with Y upward. Now, another particular force is the spring, okay? The spring force. So to find the work of the spring force, what should we do? First, we know that if we have a linear spring, elastic spring, in general, the force is given as F times F equals to K, which is the spring constant, times delta L, okay? Times delta L. And in particular, if you choose the unstretched position, as your origin, okay? So if I consider that S equal to 0 at the unstretched position, then delta L will represent what? Then delta L will be equal to S. So if this is S, okay? Since I'm counting S from the unstretched position, then S is equal to delta L. Okay, and now if I want to find the work, if I take a spring and I put a force acting on it, if I put a force on the spring to stretch it like this, okay, what will be the force acting on the spring? It will be equal to K times S. And if I want to find the total work when I displace my spring from a position S1 to a position S2, then I do integration from S1 to S2 of Ks ds. And this will give me half K S2 square minus half K S1 square. Keep in mind that S here represents the stretching or compression of the spring. So it's delta L. Okay? So now, this is what this represents the work on the spring. Okay, work on the spring. Now, if I attach a ball to the spring, let's say, if I attach a ball to the spring and I stretch my spring, then the spring will do on my ball a force that is in the opposite direction. Okay? So if I want to find the work of the spring on the ball, it will be opposite to this one. So here I will write it down. So U spring on ball is opposite to the work calculated, which will be equal to half K S1 square S1 square minus half K S2 square. And this is the one you use more. In general, you will not take the spring as your system, you will take the ball as your system. Okay? And when you want to take the ball as your system, then to take into account the work of the spring, it's half K delta L1 square minus half K delta L2 square. Now, let us take a small example. Here, if I have a cart and I am pushing it up on the inclined line, and I want to find the work of all forces acting on my system. The first step to do is to draw the free body diagram. I draw in a scheme all forces acting on the cart. So here, if I consider my cart, what are the forces acting on it? I have first the normal reaction. The normal reaction, which is always perpendicular to contact. This is the contact line here. This is my contact line. So N is perpendicular to the contact line. Okay. Now, what are other forces acting on my system? I have, of course, the weight that is always vertical, and I have the tension applied on my cord. So these are my forces. Okay. Now to calculate the total work, first I start by N. What is the work of N? Who will tell me what is the work of N in this system?
0,
Zero, very good. Why?
because it's
Of
perpendicular to motion.
displacement.
Exactly. So N is perpendicular to motion, so it cannot produce any work. Okay? So the first I say that the work of N, so U of N equals to 0 since perpendicular to motion. Okay. Now, I still have two forces, the weight and the tension. Okay? For the tension force, the work, what should I do? I should project on the direction of motion, okay, to find the work. So if I project T on the direction of motion, as you can see here, this is the direction of motion, and they gave me the angle between here is phi, okay? So if I project T on the direction of motion, what do I get? The projection is T cosine of phi, okay, and to find the work, then I multiply, if I have constant t and constant phi, then I can multiply by the distance traveled to get the work. So u of t is equal to t cosine phi times the displacement s. And why here it's a positive work? It's a positive work because the projection of t is along the direction of motion, okay. On the other hand, if I consider the weight, if I project the weight on my line of motion, it will be like this. It will be downward. Okay. So the projection of the weight is down. Then it will have a negative work. And now to project, I need the angle. And you know that this is an inclined line, and they gave me that this is theta here. This is theta. Okay. So for the weight, as usual, as we are doing usual, weight is perpendicular to horizontal, and this direction here is perpendicular to the incline. So the angle between weight and the perpendicular to the inclined is theta. So when I project on the inclined, I should do sine theta. And since the projection is in the negative direction, I put a minus. So the work of the weight is negative since it's opposing motion. So I have minus W sine theta times the displacement S. Okay? And in total, to find the total work, I do the summation of all work. and in total I will get a positive result since I am يعني if my car starts from rest, to be able to move it up, I should provide a positive work. So the balance will be positive if I am accelerating, okay? While the balance will give me a negative result if I am decelerating. Okay. Let us now do a numerical example together. We have the 10 kilogram block rest on a smooth incline. If the spring is originally stretched 0.5 meter, determine the total work done by all forces acting on the block when a horizontal force P of 400 Newton will push the block up the plane 2 meters. So here I have an initial state and I go to a final one. For the initial state, this is my initial position, so initial position of the spring, and I have several conditions for this initial position. They told me that originally my spring is stretched at 0.5, so I can say that delta L1 of the spring, delta L1 is equal to 0.5. And since it's starting from rest, so the initial velocity is 0. Okay. Now, what will happen is that a force P will push my block upward. Okay. It will push it upward until reaching a distance, a final distance of 2 meters until here. So now, when I go to my final position, what will be the new value of the spring delta? What is delta L of the spring at position 2? It is originally stretched 0.5 and I stretched more 2 meters more, so the new delta L will be 2 plus 0.5 equals to 2.5. Okay, so I have delta L1, I have delta L2, I can find the work of the spring on my box. Okay, so now let us draw the free body diagram and put all forces acting on the box. The forces are the weight, the normal, the spring force, and P. I have 4 forces. Okay, now to start with, the normal, as we said in the previous problem, is perpendicular to motion, so no work. So work of N is 0 since perpendicular to motion. Now, work of the spring, U of spring, equals to, as I told you, when you take the particle as your system, the work of spring is half K delta L1 square, so dL1 square, minus 0.5 K times dL2 square. Okay, so this is the work of the spring, and I have delta L1, delta L2, and K. All I have to do is to replace. K is 30 Newton per meter. Now, for the work of P, what should I do? P is constant, and the angle between P and the direction of motion is constant. So I should project P on the direction of motion. It is plus P cosine 30 because the projection is along the positive direction of motion. So the work of P is positive. And since P and the angle are constant, I can take them outside of the integration. And the work will be P cosine 30 times the displacement S. And here in this problem, the displacement S is 2 meters. Finally, I need the work of the weight. For the work of the weight, I can do 2 things. I can use 2 methods. Okay? We developed together that the work of the weight is minus W delta Y with delta Y upward. So we can try to apply this formula here. Minus W delta Y. Okay? If you look at, and always when you take minus W delta Y, as I told you, your Y axis is up. So here, what is delta y in this problem? Delta y is the variation in vertical direction. So this is position 1. This is position 1. This is position 1. This is position 2. Okay. So delta y is y2 minus y1. Delta y will represent the change in elevation, this distance. So if I do y2 minus y1, I get a positive result if y is upward. And the value of the vertical displacement of the block can be computed by doing the displacement s, because s is 2, and this angle is 30, so this displacement will be 2 sine 30. So I can directly say here that the work of the weight is minus W times delta y, which is 2 sine 30. Okay. Now another method to get the work of the weight, I can also do projection as we did in the previous example. Okay. So another possibility is to say I will project the weight on the direction of motion. Okay. So this is my weight, and if I project it on the direction of motion, I get a negative projection. And since the angle here is known, the angle between the weight and this direction is 30, as we said before, because look, the weight is perpendicular to the horizontal, and this axis is perpendicular to the incline. So the angle between these two is equal to the angle between these two, which is 30. So by projecting on the direction of motion, you do W sine 30, and you will put minus, because the projection on the direction of motion is in the opposite direction. So I get that work of weight is minus W sine 30. Then I multiply by the displacement S, okay, which is 2. So I get the same result of the previous method, which is minus W sine 30 times 2. Okay, so same result. So for the weight, you can or apply the formula minus W delta y, or project on the direction of motion as any other force. So now, all you have to do to find the total work is to do the summation of all work of forces acting on the body. And you will expect that the summation of work will be positive or negative. Positive, because your system is initially at rest. And since you are displacing it up, this means that the work should be positive. Because if you don't have a positive work, you cannot go from rest upward. Okay? On the other hand, if you move at a velocity, at an initial velocity, and the velocity is decreased, then the sum of work will be negative. Now we will introduce the principle of work and energy. The principle of work and energy will relate work of forces to variation in kinetic energy of the part. Okay? And to derive this theorem, we start from the kinematic relation that ATdS equals to VdV. If you remember, in the first chapter of dynamics, we said that ATdS is equal to VdV. If we take ds to the other side, then AT is VdV over ds. Okay? Now, why we will use this result? Because look, we said that if we have motion, okay, the forces that will do work are only the forces which have component along the direction of motion. So here, for example, if you are working in UT-UN frame, if you have a force resultant Fr, you can decompose it into two components, one along UT, tangential to the path, one along UN, directed towards the center of curvature and perpendicular to the path. But we know that for work, the forces that will do work are only the forces along that has projection along motion. So here, only sum of t will do work. Sum of n will not do any work because sum of n perpendicular to motion. So we can say that the work of the forces Fn is equal to 0 because they are perpendicular to motion. So when we want to calculate the summation of work of external forces on a particle, we only account for Ft. Okay? So let us compute what is the sum of work of Ft. So to find the total work of external forces, it's summation of integral S1 to S2 when we move from position 1 to position 2 of Ft ds. But you know that Ft is what? Ft is simply sum of Ft. When you do summation of Ft, you can replace Ft by MAT. Okay, so and AT is what? AT is VdV over ds. Okay, so if you replace Ft by MAT, which is M VdV over ds, and then you multiply by ds, ds will be simplified, and what you will get only is MVdV. So you can say that sum of work of external forces is equal to integral from V1 to V2 of MVdV. And if you integrate this term, you get half MV2 squared minus half MV1 squared. This means what? This is the principle of work and energy. This principle states that summation of work of external forces on a system when going from position 1 to position 2 is equal to half mv2 squared minus half mv1 squared. So the sum of external forces of work of external forces is equal to the variation of the kinetic energy. If the total work is positive, the velocity will increase. If the total work is negative, the velocity will decrease. This is why I told you when summation of work is positive, then my system is accelerating. And when summation of work is negative, then my system is decelerating. And in general, the notation used in English system for kinetic energy is T. So T represents the kinetic energy. So I can rearrange my principle of work and energy in this form, that the initial kinetic energy plus summation of work of all external forces is equal to the final kinetic energy. Now, if I take a system of particles, so I can work with several particles instead of one. So all I have to do, if I take a system of several particles, I say that summation of kinetic energy of all particles at state 1 plus summation of work of all external forces on the system is equal to the final kinetic energy, summation of final kinetic energy of all my particles. So let us now take a certain example. If you have a block and it's moving under the effect of force P and the surface is not smooth, so you have friction. So what will be, if I draw the free body diagram, I have the friction force, and here it's a kinetic friction since my block is moving, so F kinetic. And I have the weight and the normal. But of course, when I apply the work and energy principle, the weight and normal will not be included because in this example, both are perpendicular to motion. So when I do work and energy, I only have the work of P and the work of the friction. And as you can see, P is along motion, so it will produce a positive work, while friction is opposing motion, so it will produce a negative work. And given that we take Fk here and P constant forces, then we can say that their work is simply the force times the displacement because they are along the direction of motion. So if we apply for this simple case the principle of work and energy, we have that half mv1 squared, which is the initial kinetic energy of the block, plus the force P times the displacement S, which is the work of P, minus mu kn times S, minus because the work of the friction is negative, and we have mu kn times the displacement s equals to the final kinetic energy of the part. So this relation, you can give you V2 if you know the distance s, you can find what will be the final velocity after a certain distance s of the part. Let us do a numerical example. The 17.5 kilonewton car is traveling down the 10 degrees inclined road at a speed of 6 meters per second. If the driver jams on the brakes, causing his wheels to lock, determine how far as his tires skid on the road. The coefficient of kinetic friction between the wheels and the rod is 0.5. So always, when you have initial and final state, try to think about work and energy. So here, this is the initial position. What do we know about the initial position? V is 6. So we can say that V1 is equal to 6 meters per second. And they are asking for the distance moved before the car will stop. Okay, so the car will stop when V is 0. So we know that at the final state the velocity is 0. So since we know the initial and final velocity, so we know the initial and final kinetic energy, we can think about using the principle of work and energy to find the value of S. Okay, so the first step in such problems is to draw the free body diagram of forces acting on the car. So what are the forces acting on the car? I have the weight, W, and this angle between W and Y the perpendicular to the incline is 10 degrees, as usual. So this angle is equal to this one, because the weight perpendicular to the horizontal and this direction perpendicular to the incline. And we have the normal and we have the friction force. Okay, so now if we want to apply the principle of work and energy, what is the equation we can write? We can write that half m here is 17.5, so half times the mass, which is 17.5, and pay attention for units. Okay, so here you should convert to Newton, so times 10 to the power 3 to convert to Newton. And guys, here don't forget to divide by G because you need the mass. Okay, when they say 17.5 kilonewton car, this means that this is the weight, and what you need is the mass, so you should divide by G, which is, we will take it as 10. So this 17.5 times 100 will be the mass in kilogram. Okay, now V1 V2 is, when we apply the work and the energy, we start by half mv1 square. V1 is 6, so half m times 6 square, which is 36. Okay, plus now what? Plus sum of work of all forces acting on the car. What is, so I should take the work of normal plus the work of the friction, okay, plus the work of the weight, plus the work of the weight, equals to what? At the final state, I have 0. I have 0 velocity, so 0 kinetic energy. So this is the relation I should apply in this problem. To be able to solve for the distance s, I should find the work of my forces function of s. To start with, the normal is perpendicular to motion, so no work. I can directly simplify work of the normal. I still have the work of the friction and the work of the weight. To start with the friction, as you can see, the friction is opposite to motion, so it will have a negative work. So I can say that work of friction is minus the friction value, which is mu kn, okay, times the distance of displacement, which is s. Now I need to find n, because to calculate, to find the work function of s only, I need to find n. And how to find n? What should I do to find the normal reaction? To find the normal reaction, I will apply the second law of Newton in y direction. Okay, so here, if you project on y-axis, sum of y equals 0 because your motion is along the incline, so no motion along this direction. If I call this is, if this is my y, then I can say that sum of fy equals to 0. And if I do projection, I have the projection of the weight. Okay, and we said that the weight is doing an angle of 10 degrees with, so here, if you want, let me show it again. Okay, this is the y-axis I am considering, perpendicular to the incline. This is the weight. The angle between them is 10 degrees. So when I project on this direction, I get minus w cosine 10 plus n equals to 0. So I did use that n is equal to w cosine 10. Okay, so now I know the value of n. I express the work of friction function of S. And finally, I have the work of the weight. To find the work of the weight, for the work of the weight, I can here also, as I did previously, I can do two methods. Here it's easier to project on the direction of motion. Here, because I'm moving downward, the projection of weight will be in the positive direction. So the work will do a positive work. And since this angle is 10, so the projection is plus W sine 10. So I get equal to plus W. And of course, since it's a constant force and constant direction, so the work is W sine 10 times the distance S. So now I expressed the work of all my forces function of S. All I have to do is to replace back into the principle of work and energy, and I can get S. Okay, so here if you replace back in the theorem we wrote together, T1 plus sum of work from 1 to 2 equals to T2, you get your only unknown, which is S. So in general, when you have a displacement that is not known and you know the initial and final velocity, you can use the work and energy to solve your problem. Of course, we can use the previous chapters, but here you solve in one step. For the previous chapters, you need to find the acceleration and then use a formula relating acceleration and displacement to find displacement. So it's also feasible. You can use the previous chapters, but work and energy is easier. Try to solve this problem using the previous chapter as a practice. So now I will open a new session to continue, okay?